Okay, so let me first talk to you guys about the concept of Lewis dot structures, since this is going to be like the freebie easy points for you when you take the test tomorrow. And so Lewis dot structures are a shorthand way of showing the valence electrons associated with a particular atom. So if we take, for example, TC, you want to go to lunch?
Yeah.
All right, hold on, you guys. I'm going to put this on pause and come back after lunch. Wow, I'm having serious problems here, you guys. The Viddle just totally shut down on me. So let's hope that I can get this to work now. The group 1As, you know that there's one electron in the valence. Here we have 2 electrons in the valence, 3, 4, 5, 6, 7, and then a full octet of 8 in the noble gas core and the noble gases. And so if we want to represent these numbers with a Lewis dot structure, it becomes a pretty straightforward thing. We take, for example, boron right here. And if I have boron with a chemical symbol, I need to be able to show that there are 3 electrons surrounding in the valence shell of boron. So I simply create this situation. Okay? And let's say I have nitrogen, which has 5 electrons. I'm going to go ahead and fill the 4 corners first, and then I'm going to put 1 paired up, just like I've shown there. Oxygen, do the same thing. We know there are 6, so I'm going to put the 4 in place, and then I'm going to pair up 2, and conventionally you do it on opposite sides of each other. And I can continue to do the same thing. Let's take fluorine, where we know we have 7 valence electrons, and I'm being naughty here. I'm putting them in very quickly, but you can see here that I have fluorine showing its 7 valence electrons. I want you to imagine what neon would look like, and also to take a look at hydrogen. Hydrogen, you're just going to have the single valence electron. Hello! Hello. Kathleen Wallace just walked by and wondered what I was doing. It was actually at Loomis. Downright goofy. Hold on, I'm going to pause this. Okay, so there we go. That is the concept of doing Lewis dot structures, and you're going to be using them quite a bit as we move forward, but make sure you get these free points on the upcoming test. All right, let's shift gears now. We are going to talk... People are harassing me. Hold on. All right, so let's shift our attention to the group quiz. And you guys said you needed the answers for number 1 and for number 5 because you hadn't shared out this information yet. So let's take a look at 1. And the first question is, explain why the atomic radius of rubidium... Let me lock this out here. This is way too thin. I got to get it fatter. There we go. Okay, erase that. So rubidium, Rb. Why is it that the atomic radius of rubidium is larger, so I'm going to go ahead and draw it as a big thing, than the atomic radius of potassium? Okay, and if you look at the periodic table, let's go backwards here, and you look where rubidium is, and you compare that to where potassium is, you can see that potassium is higher up than rubidium, which means that it actually has a lower principal quantum number. So don't forget, if we label these things by their principal quantum numbers, that rubidium has a principal quantum number of 5 versus potassium 4. So as I've used in the past, it's as if rubidium has an extra layer, a couple layers of jackets, not a couple, 1 layer of jacket more than potassium. And so it has orbitals that occupy higher energies that are further away from the nucleus, and therefore that's why the atomic radius for rubidium is bigger than that of potassium. So that's A. For B, why is it that rubidium, okay, has a larger atomic radius than strontium? And that's an R, sorry. So if we go back in here, you can see that rubidium is back here, and then let me just erase that stuff here. Okay, and actually I can erase all that since it's going to be inconsequential. Here's our rubidium, here's our strontium. So instead of being above rubidium, as was potassium, strontium is now to the right. Okay, and if we go over here, we understand that as you move from the left to the right, you increase the number of protons. in the nucleus of that particular atom. And don't forget, protons have an attractive force associated with them with regard to electrons. So that means the larger, more attractive force you have, the more you're going to be able to draw your cloud of electrons towards yourself and towards that nucleus. So that's why strontium has a higher attractive force for the electrons that it contains, and we'll be able to pull them closer as a result. Okay, and then letter C. If ionic size increases as you go from right to left across the period, why is the ion of carbon so much smaller than the ion of nitrogen? So for this, here, let me take a picture and then add it. Okay, so I've just imported a screenshot, not a screenshot, a photo of partial periodic table. And if we take a look here between 4A and 5A, that's going to be an important piece because that's where we're talking about the difference between carbon and nitrogen. Since carbon is going to be, let me change it to blue, right here, and nitrogen is going to be this dude right here. Nitrogen forms a -3 common ion, whereas carbon forms a +4. So don't forget, what that means is you've lost 4 electrons. And if you lose 4 electrons, you lose the repulsive forces associated with those electrons without changing the attractive, appreciably, without it changing the attractive force of the nucleus. And so all the electrons that remain are going to get pulled in much closer. Okay, so we lost the repulsive forces without appreciably changing the attractive forces. That shrinks the entire ion. The exact opposite is happening at this point. So this is the breaking point that exists right here with nitrogen, because in the case of nitrogen, you're adding electrons. And if you're adding electrons to this whole thing, the repulsive forces increase among the electrons in that cloud, and they spread further away from each other, and therefore it gets much bigger. So despite the fact that in general the ion will increase as you move in the direction that I just drew that arrow, because you go over from being an anion to becoming a cation between nitrogen and carbon, that's why you're going to have that significant difference that exists in size. Okay, let's now scooch to the last question, which is question number 5, where electronegativity is the question. And the question asks, electronegativity is an atom's willingness to attract electrons when the atom is involved in a chemical bond with another atom. Map the trend of electronegativity on a blank periodic table. If one atom of hydrogen were to bond with one atom of bromine, which atom would pull more of the electrons? So first, let me go ahead and import the periodic table once again. Make it a little bit bigger here. Okay. So in terms of electronegativity, it increases, I'll use black here, as you move from the left to the right. So that's increasing electronegativity. And it also increases as you go upwards to a lower quantum number. So this is also increasing electronegativity. Okay, so that's the first part of the question. Now I can't remember the second part. Let's see. Okay, if one atom of hydrogen were to bond with one atom of bromine. So hydrogen's over here, so we have a relatively high electronegativity, and bromine's over here, which is also a relatively high electronegativity. So then you have to say, what? How do we deal with that? Well, it's important that you go and look for the electronegativity specifically associated with these things. And again, if something has a high electronegativity, that means it attracts a lot of the electrons when it's chemically bonded with another atom. So if I were to draw HBr, which is an acid actually, this would be what it looks like. And if I were to draw it in terms of a molecular model, it would look like this is the H, and this would be bonded to the Br. And the question I have for you is, where would you start to see the electrons? Would they move towards the bromine side? Or would they move towards the hydrogen side? And the only way you can do this is to look up that number. In this case, bromine has an electronegativity of 2.8. And hydrogen has an electronegativity of 2.1. So that means bromine is going to have greater attractive power for the electrons. So if I were to draw an electron cloud as sort of this green here, it would look like this. You'd have more electrons associated with the bromine side of this atom, or this compound that you've just created. Okay, so it would pull those electrons towards the right side of the compound. All right, what was the other question? Oh yeah, so what is Hänkelbrief? Hänkelbrief is a set of nonmetals that are, they happen to be fairly high in terms of their electronegativity as a group. But what's very important about these things is that hydrogen, and this is what I mean by Hänkelbrief, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. These things are all found in nature as what are called diatomic molecules. They're never found individually. Like, you don't find an individual H ion floating or atom floating around. You always find two of them. And so all these dudes have two of them associated with them. Now, this is less important than to associate this with electronegativity until you look at the concept of the fact that these all have the same electronegativity. So that means, obviously, you're going to have two hydrogen atoms which both have a electronegativity of 2.1. So if you were to draw the electron cloud around these, it would be evenly spaced. And whether that was hydrogen or oxygen or nitrogen, chlorine, bromine, iodine, and fluorine, all of them would have no bias towards one side or the other because, you have the same electronegativity associated with both atoms since they're both the same atom. Okay, hope this all helps you guys. I'll see you tonight for the review session. Bye.